Welcome to the crypto seminar, guys. Today we have Binyi. He's going to talk about his recent work with Dan on Lattice-fold and its application to Succinct proof systems. Welcome.
Thanks for the introduction. Can everyone hear me clear in the Zoom? I would suppose so. Okay, great. Cool. Yeah, so let me get started. It's great pleasure to be here at CMU. Today I'm presenting Lattice-fold, which is a new construction of folding scheme that allows you to construct very efficient proof systems for large statements. Okay. Let me start with some background and motivation about delegating computation and SNARKs. Suppose Alice, she has a very old iPhone, say iPhone 3, okay? But she wants to perform some computationally expensive tasks. And this task also involves some large secret witnesses information that she doesn't have access to, okay? For example, she might want to ask ChatGPT some questions, but she doesn't have access to this large language model that OpenAI has. So to do this, she can send her question to the cloud server of OpenAI, and the OpenAI's cloud server will be responsible for computing the function and return the answer. But this raises a question. How does Alice know this is the correct answer, right? What if it's just some junk information or some faked answer? And a classic solution for this is to ask the prover to attach a very short proof called SNARK proof, or succinct non-interactive argument of knowledge proof. The correct verification of this proof implies that prover actually knows the correct witness and the computation was done correctly. Moreover, one is proved to be very small and also very cheap to verify. So the Alice, even given an iPhone 3, can immediately verify that this is the correct answer. Beyond this example, there are tons of applications for SNARKs in scaling blockchain, in obtaining verifiable machine learnings, verifiable fully formed encryptions, and there are even more sophisticated and exciting applications for that. And all these exciting applications requires the prover to generate some proofs for some very complex statements, like machine learning inference tasks or ZK rollup transactions and so on. And our goal here is to enable the prover to generate this proof as fast as possible. Before describing our solution, I would want to overview the state of the art in practice. And I would categorize the set of solution in two classes being used in practice. The first one, I would call it monolithic SNARKs, which enables you to generate a proof all at once given certain statements. And in the literature, we have so many such kind of candidates. Many of them actually works pretty well for certain tasks, like proving the correctness of several hashes, like 10,000 hashes, and or proving a correctness of some circuits over, say, 2 to the 18 gates. However, when it comes to prove some very large statements, this now becomes more problematic. And the issue here is that for those kind of SNARKs, you have to generate a witness first in order to even start this SNARK proofing process. To illustrate, let's consider an example where the goal is to prove the correct block state transitions with respect to some block of transactions. And to do this, the prover really have to gather all these transactions information and re-execute these Ethereum transactions, for example, and obtain some program execution transcript and transform this execution transcript into a very long vector field elements. And only then she can start doing the proving. And usually for many applications, actually this can be an expensive process. So you already waste a lot of efforts and time to do this before you even start doing the proving. So that's the first limitation. And second, because you are proving some very large statements, this extended witness will also be huge. And you have to feed this into SNARK machine, so that requires very large pool of memory. And also, usually, unless the SNARK scheme itself is very parallelization friendly, it's also hard to do parallelization. Given that, an alternative way is to build a piecemeal SNARK, what I would call. At a very high level, the intuition is the following. So you start with some very large MP statements you want to prove. But suppose magically, you can split these large statements into many small chunk statements, okay? Suppose, for example, you want to prove the correctness of 10,000 transactions. You can split them into 1,000 chunks. Each chunk statement is just be responsible for 10 transactions. But this is just a toy example. It's not that trivial to like translate arbitrary arithmetic circuits into many small chunk statements. But it turns out recently there's a work called Mangrove that exactly achieved that in a very efficient way. But this talk, I won't talk about that, but let's just assume magically we can split a large statement into many small chunk statements. And now the goal is to prove the correctness of all these chunk statements, right? And our strategy is to use SNARK recursion. So the idea is to generate this proof recursively from the leaf layer to the root layer of this tree. So you have this kind of many chunk statements you want to prove, you build a tree, and you start from the leaf layer, and for every leaf statements, you generate some, say, more holistic SNARK proof for the chunk statements. For example, here for statement 1 and statement 2, you generate 2 proofs. And then in the next step, you'll do generate a recursive proof for their parent nodes, which checks 2 things. First, the chunk statement at these parent nodes is correct. And moreover, you also check that these 2 proofs generated by the 2 children are correctly verified. And this implies that all of these 3 chunk statements are correct. And you don't have to stop from here, right? You can do this recursion again and again. And finally, you obtain a SNARK proof for the root nodes. And this root proof now implies that all the chunk statements in this entire tree are correct, which implies the original large statement is correct.
Does the graph structure have to be like a tree? Can it be like a DAG or something?
Yeah, it can be a DAG. It depends on you. This is just a simple example. Yeah. So it has this obvious advantage of having much smaller memory overhead, which is only related to this chunk statement size. And it's also very streaming friendly and parallelization friendly because you can compute the path proof compute the proof along each path of the tree without affecting other paths. But unfortunately, actually in practice, this kind of scheme is not widely used. The reason is that they have really large recursion overhead here for 2 reasons. The first reason is you can see for every recursive step, you have to generate SNARK proof. So that in total, you have to generate so many SNARK proofs. And SNARK proof generation is never a very lightweight process, right? So that's kind of time consuming. And secondly, you see that for each recursive proof, you also prove something which is concretely complicated. So beyond checking these chunk statements, you also need to embed SNARK verification logic inside to verify this pi1, pi2 are correctly. So that even for each recursive proof, the statement size can also be large. So for these 2 reasons, this is not very practical. So recently, there are many elegant works trying to build a folding scheme, a new primitive called folding scheme, trying to reduce this recursion overhead. So what is a folding scheme? So in the folding scheme, the folding prover will have access to 2 MP statements, while the instance will consist of a very short commitment to a very long witness that satisfies some MP statements. And now the prover, the goal is to convince the verifier that he knows the correct witness for these 2 statements. And to achieve that, he will run some very lightweight public coin protocol. And at the end of this protocol, if the verifier accepts, he'll generate some folded single statements, which can't merge these input statements. And the corresponding folding prover will also obtain a correct witness for that. So in some sense, you see that this protocol serves as a protocol that enables to merge 2 statements into one, right? You kind of reduce the checking of 2 statements into the checking of 1 statement. But don't have to stop from here. We can even generalize that, which leads to this notion of reduction knowledge, which was introduced by Abiram and Brian Pownall in 2023, which is a very elegant work. And here, the idea is that this reduction knowledge protocol allows you to reduce the checking of some input statements in some input relation R1 into the checking of some output statements in relation R2. And you can see here, the folding scheme is just a special case, right? Well, this R1 is just the product of some MP relation R by R, and the output relation is just R. And we'll go to just reduce the checking of 2 statements in R to 1 statement in R. And you have to satisfy this completeness, meaning that in an honest execution, if the input statements is in the relation, then the prover should also be able to generate the correct witness for the output statements in the relation R2. And they also satisfy this knowledge soundness, meaning that for possibly malicious prover, if he's able to generate a witness for the output statements, that implies that he also knows the correct witness for the input statements. By knowing, I mean there exists some extractor algorithm that outputs it given a black box access to this malicious prover. So now let's see, suppose we have folding scheme, how do we build a piecemeal SNARK? So here, let's assume that we can split these very large statements magically into many chunk statements, say n different chunk statements. And our goal is to prove the correctness of all these n chunk statements. So now for the SNARK prover, given these folding schemes, the idea is to initialize some statements, folding statements here. And at each step, he'll run this folding prover algorithm to merge the statement he wants to prove onto these folding statements. So in the first step, he'll merge C1W1 onto these statements to obtain a new folding statements. And the second step, he'll do something similar to obtain the new updated folding statements. And do this again. And finally, he'll obtain a single folding statements that's already merged all these n-chunk statements he wants to prove. And now you can use this as a proof, right, to send to the verifile. And the verifile now only needs to check these single folding statements. And by the property of folding scheme, this implies the prover actually knows the correct witness of all n-chunk statements.
Can I think about the old way to do this? So the original way is that you embed like a verifier circuit inside of that statement or something.
Yes,
So
yes.
that's kind of like one way to implement this folding.
That's kind of different. Like SNARK scheme is kind of different from folding scheme, right?
I know.
Yeah.
I'm just saying that is that like a special case of like doing folding? Can you think about it?
You might be thinking about that. Yeah, maybe. Yeah. But I would say that you'll find out why this is actually a better approach compared to that SNARK recursion. Yeah. So, right. And actually, this kind of scheme is not actually correct, actually. So one minor caveat here is that the verifier actually doesn't know whether the proof being sent is having correct commitments, whether this short commitment is correctly computed and is consistent from this C1 to Cn, right? It might be some arbitrary folding commitments. So to solve that, there's a very easy fix. Well, let's say there exists some trusted public inputs, which is the hash of this Chen hash of this C1 to Cn. And then we just let the prover to additionally send this C1 to Cn to the verifier along with this proof. And then the verifier can just check that public input is consistent with all these n commitments, and he can recompute the right folding commitment herself and do the final check, right? However, this is not gonna be efficient because the proof and verifier complexity is now at least linear to the number of chunks. And when the number of chunks is large, it's actually pretty expensive. But we can do much better and remove the dependence on this number of chunks. And the idea is pretty simple, pretty similar to SNARK recursion, where you just delegate this kind of verifier work, this iterative verifier work to the relation you want to fold. Okay, so what does that mean? So now in this new solution, as before, the prover at each folding step will fold these two statements he wants to fold and obtain a folded commitments and a witness. In the next folding step, he'll generate a new statement, online statements to be used to folding. But here is slightly different. Before it's just this chunk statement CIWI, but now these statements also includes this folding verification procedure that merges two commitments to the one commitment. So here it makes sure that not only this chunk statement is satisfiable, but this folding verification procedure is also done correctly. So you can make sure that this folding commitments is correctly computed at each iterative steps. So that means at the end, the folding SNARK verifier only needs to check these folding statements, which already implies that all the computation was done correctly in each step. So go back to Ming-Xun's questions before. Why is this better than a SNARK recursion, right? Why is it more efficient? It's more efficient for two reasons. First is that this folding verifier usually is very simple. It's just a linear combination of these short commitments. And this is much simpler than SNARK verifier. So that implies that these recursive statements you want to fold is actually much simpler and much smaller than the recursive statements you want to prove previously. And the second reason, which I think is a more important reason, is that for each step, the folding prover, what he needs to do, he doesn't even need to generate SNARK proof. What he needs to do is after generating this extended witness, he only needs to do a very simple linear combination of this witness vector, which is much, much faster than the SNARK prover. And these are the two reasons why a piecemeal SNARK built from folding scheme is much, much more efficient than a regular SNARK recursion.
when you say they are only doing some linear operation, is it true for all folding scheme or it's just like a special case?
For now, almost every folding scheme is doing that, I think. Yeah. Yes. So now the question is, how do you instantiate a very efficient folding scheme, right? And we do have many very good solutions. And for almost all kinds of this scheme, the empty state we fold has the following format, where the instance will consist of some short commitments. And this commitment has to satisfy two properties. First, it enables you to compress a very long vector into a short string. And second is linear homomorphic, so that the folding verification is super easy, just linear combination of commitments. And all existing schemes before this work are using Peterson commitments, which is linear homomorphic, pairing-free, and transparent, which is pretty good. However, they also have their own limitations. In terms of security, they are based on this discrete log assumption that's vulnerable to this Strauss attack and therefore not post-quantum secure. And in terms of efficiency, they also have kinds of limitations. First, in order to obtain relatively efficient construction, we have to use this so-called pair of cycle curves, unless you use some other optimizations. And then this kind of pair of curves usually is harder to find, harder to implement, and also slightly less efficient than regular curves. And then second, because of the use of commitments, that means the prover has to perform a lot of elliptic curve scale modification over a very large field, because this field should be crypto secure, like usually 256 field. So first, this is very expensive. And second, it's also kind of wasteful, because in the real world, usually the data units are some very small integers, like 32-bit integers, rather than like 256-bit scalars. And finally, in terms of this recursive folding verifier, you also have some overhead here. The first overhead, you have to represent these elliptic scale modifications, which is a bit expensive to represent as arithmetic circuits. And second is that beyond checking this elliptic curve operation over the base field of curves, there are also some other operations, which is lying on the scalar field of the curves, which is a different field. That means this circuit has to simulate this field operations in a different field, which implies that you have to simulate a lot of range checks, modulus reductions, which makes it also slightly more complicated and less efficient. So given that, we may wonder, why not just use some alternative way to do that? Let's just use a Phi-based SNARK and do recursion, right? For which you can get rid of these non-native simulations. But as I said before, this involves to use some full SNARK recursion, which is less efficient than using this folding scheme-based piecemeal SNARK. So our goal is still, we want to have a very efficient folding scheme. And the question is whether we can construct such a scheme that's also plausibly post-quantum secure. And here's our main contribution. We introduced this LatticeFold, which is the first lattice-based folding scheme that's based on this MC's assumption that's believed to be quantum resistant. And second, and even more exciting, that is actually very competitive in terms of efficiency, even compared to these existing pre-quantum folding schemes. And one thing to note here is that you can actually use some kind of underlying field that's actually relatively small, like 32-bit field or 64-bit field, which makes it even more efficient. Okay, so now let's go to the technical part of this talk. Before that, just let me know if you have any questions. Okay, yeah, let me wait for a bit.
So is it like you just change a commitment scheme, or you completely change a commitment scheme and also how do you do?
Both. So basically, we want just change the commitment scheme, but after changing the commitment scheme, in order to make it work, you need to do something more. So now our goal is to obtain folding scheme for this MP relation. But in this talk, I will focus on a simpler problem. Let's just focus on this folding of this commitment opening relation, which will already cover most of the ideas. And I want to note that even just for this is already very useful in the sense that it leads to some batch proof of knowledge for short pre-image of some linear maps like matrix applications, which has a lot of application in the lattice world. And this leads to the first, first scheme that's without relying on some so-called relaxed binding property and leads to a much more efficient scheme than all existing works. Okay, so now the first task we need to figure out is that what kind of commitments we need to use, right? So recall that the two properties we want is that first, you need to able to compress a long vector into a short string. And second is that this should be linear homomorphic. And in the lattice world, the first scheme to come to mind is this Ajtai collision resistant hash functions. Now, forget about hiding. For this talk, I just focus on the binding property. So I'll explain what Ajtai is. But before that, let me have one note that is Ajtai hash function is actually pretty efficient. With correct optimizations, it can even approach some performance of widely used hash functions used in the blockchain industry. So how does it work? So usually here, the message would be an integer vector of length n, where each entry will have small absolute values. A typical example is just binary vector, and it will go to commit this long binary vector. And to do that, we will multiply it by some public random matrix A over ZQ. And then that will lead to some very short string, which is your commitments. So it satisfies compressing property. And it also satisfies this binding property, saying that it's hard for you to find two messages that maps to the same commitments. And this is based on this SIS assumption, saying that given public random matrix A, it's hard to find a small norm vector X such that AX equals 0. To see why it leaves binding property, suppose for contradiction, you have W1, W2 that maps to the same commitments. Then W1 minus W2 is a SIS solution, which is small norms, right? And also it satisfies this linear homomorphic property as long as the coefficient is small, because this follows from the linearity of matrix multiplication, which is pretty straightforward. And one thing to note here is that in practice, you will never use this scheme, which is actually very inefficient. Usually what you do is replace this integer with a polynomial ring and replace this CQ with a quotient polynomial ring so that it can pack more information into one ring elements, and you can replace these expensive matrix multiplications with some ring operations that's basically using NTT or FFT to make it much faster. But here, I'll just focus on this integer solution just for illustration purpose. Yeah, so now the goal is the following. We want to build a folding scheme for this Ajtai commitment opening relation, right? And this commitment opening relation consists of all these tuples, which consists of a short commitment C and a witness vector W, for which C equals A times W, and the infinite norm of W is also small, meaning that for every entry of W is smaller, the absolute value is smaller than some parameter beta here. And now let's say we have two statements in this relation. Can we merge them into one relation, right? How to do that? And there's a very easy and naive way. You just do, whenever you want to do folding, you just do randomly combination. And however, in the last word, this is not gonna work, because after the folding, this will no longer be in this relation. The main reason is because this norm blow up. Let's say even R is just 1, you are even just doing addition, you can go from norm from beta to 2 beta, right? And things can get worse if R is larger. And this means that after a very few number of folding steps, this norm will blow up very quickly and suddenly exceed some threshold so that commitments are no longer binding. Actually, there are also some concrete attacks for that. So we want to achieve some stronger property. We want to make sure after folding, they will be still exactly in the same relation. So to achieve that, our first thought is the following. Well, we know that this W1, W2 are having norm as large as beta. Why not refreshing it a little bit and massage this input witness bit to make them even smaller before we do this randomly combination? However, to instantiate this intuition, we have to use a very nice property about reduction knowledge protocol, which is that it allows composition, which is showing in this paper. So basically, suppose you have a protocol that reduces a relation R1 to R2, and another protocol reduce R2 to R3, then you just compose them together, then this will give you a reduction from R1 to R3. And now in this folding scheme, our goal is to reduce the checking of two statements in Ri type beta to 1, right? And our goal is to construct such a protocol. And we split that into two parts. Well, the first part, what we do is that we split these two statements into 4 statements. And why we do that? Because after splitting, I can make sure that for each of the statements, this witness will have even smaller norms. Okay, and after that, we'll do this random combination and design a very careful folding scheme so that we can like fold this 4 statement back to 1 statement, that the norm is still less than Ri type beta. And then you compose these together, That's exactly what you want for pi, right? So now the question is how to instantiate, decompose, and fold. And we start with the decomposition part. We split 2 statements into 4 statements. For simplicity, I'll just explain how to split 1 vector to 2, but idea can easily generalize from 2 to 4 or even more general. So now in this case, we see that we have some input statements for which the witness is an integer vector for which every entry is in the range between minus beta and beta, right? And now our goal is to split them into 2 vectors that have smaller norms. So how to do that? Actually, it's pretty easy. It's very similar to this gadget decomposition tricks in FHE. And basically, the idea is to write this big norm vector using some small base B. So more precisely, what it means is for every entry of W, you do a division by this parameter B, which like B also satisfies B squared equals beta in this case. And then that will give you some remainder and quotient, right? And this vector of remainders and the vector of quotient will be exactly the vector you want. And they will definitely satisfy that every entry is in the range between minus B and also minus B and B. And another nice property here is that if you multiply matrix A on both sides, this equality still holds. So this gives us a way for the folding verifier to very quickly check this linear combination homomorphically. So this leads to some very nice reduction knowledge protocol where the prover, given some input witness, and try to split this witness into 2, just run this splitting algorithm, obtain W1, W2, computing the commitments C1, C2, and send to the verifier. The verifier just check that C1, C2 are consistent with input commitment C. If yes, output C1 and C2. So it's easy to see this satisfy completeness, right? Because W1, W2 are correct opening of C1, C2 for output statements. And it actually also satisfy knowledge soundness easily because for any witness W1, W2 that's in the output relation, you just extract as a linear combination of W1, W2 to obtain W star. And it's easy to see that actually W star is also a correct opening for input commitment C that has a norm no more than beta, okay? Any question? Okay, so we have finished this first step. We'll split 2 statements into 4. And now is the more interesting part where we want to merge 4 statements into 1. And also for simplicity, I just focus on 2-to-1 folding, but 4-to-1 folding can also be achieved, even though the analysis is actually much more complicated, which I want to explain. And for 2-to-1 folding, you see here we are in a better situation where this input witness now are having smaller norms rather than beta, it now is just B. So that means as long as we do random combination carefully, we just use some small random scalar, we can make sure this blow up won't be too large, right? You won't blow up to more than beta. So it's easy to achieve completeness to make sure after folding, the witness is still in the relation of beta. However, unfortunately, this doesn't satisfy knowledge soundness. To illustrate, let's consider a typical way to do extraction. And here, we just consider even simpler problem. Let's assume this malicious prover is almost perfect. It can output some correct witness for any randomly folded commitments. And that means we can feed it with 2 different random challenges, and he obtain some witness that's correct for the output statements. And recall our goal is to recover the input witness, W1, W2, for the input commitment C1, C2 in this extraction process, right? And here the naive way is the following. We just build this kind of system of linear equations and try to solve W1, W2, right? And even better, you can actually have some closed form formula for W1, W2. And the hope is that that would be exactly the witness you want to get. And hopefully they are exactly in this input relation. But unfortunately, that is too good to be true. And this witness will actually not be in the input relation R type B. And the issue is, again, about the norms. You see here, even in this closed form formula, the left-hand side term is a difference of 2 vectors whose norm can be as large as beta, right? Because the output relation has a parameter beta. And if you do the difference, they can be as large as 2 beta, which is already much, much larger than this small parameter B here. And these things can get even worse if you multiply the right-hand side, which is even larger. So in some sense, this kind of a random combination and naive extraction actually doesn't work, because if you do this naive extraction, finally you get something large. And this is actually some problem that has been like haunted a lot of lattice researchers for many years. And we'll try to fix it, okay? And the idea here is we add something else. We add a range proof on top of it. And the hope is that after adding this range proof protocol, we can actually argue that this extract witness will actually be small. So let me be more precise. So the main goal here is for the prover to construct some proof of knowledge protocol such that given some two input commitments, C1, C2 for folding, we want to prove the knowledge of some committed witness, like some witness vector, that satisfy three things. So first, it satisfies matrix multiplication relation for Ajtai. And second, very importantly, you have to make sure this witness are having small knobs. Basically, every entry Fi should be in the range between -b and b. And finally, we want this proof of knowledge protocol to have a very efficient verifier, which is very important for having an efficient folding verifier to be embedded later in the recursive relation. Okay, so we achieved this by combining this previous random combination plus some range proof protocol. So the question is how to instantiate this range proof protocol. And oh, by the way, so given this, first, this matrix multiplication relation is actually pretty easy to achieve. You can directly achieve that using this rewinding-based extraction and random combination. But difficulty part is this range check part to make sure that this witness is actually having small knobs. And that's what range proof protocol is about. And we achieve this in two steps. The first step is to rephrase these range proof statements as a sumcheck statements, which I'll explain what sumcheck is later. And after that, we'll build an efficient folding protocol for these sumcheck statements. Before that, let me quickly overview what sumcheck is. It's actually pretty interesting because as a history note, it's actually some very theoretical work. It's like dating back to 1992, its main functionality is prove some very famous complexity theory for proving that polynomial hierarchies in IP, which also inspired the proof for IP equals P space. But subsequently, there exists so many very nice optimization for this protocol to make it actually very concretely efficient. And now it's one of the most popular scheme, like approach and techniques to be used in industry, which is kind of an amazing story on how this theory and practice can connect together. So what is sumcheck? So the sumcheck problem is formulated as follows. So we'll have some committed multivariate polynomial, say with m different formal variables, and the goal is to convince the verifier that for this polynomial, the sum of the evaluation of this polynomial in this Boolean hypercube, which is 0, 1 to the m dimension Boolean hypercube, equals some claim value s. Okay, and there's a very easy way to achieve that for verifier, right? So verifier just query this polynomial at every point in the Boolean hypercube, and then check the sum, and that's finished the proof. However, this is very inefficient, where the verifier complexity is at least the size of Boolean hypercube, which is pretty large. And we can do much better, which exactly this sumcheck protocol does. So it is a multi-round, basically m-round interact protocol between prover and verifier, where in each round, the verifier will sample and send some random challenge field elements to the prover. And in some sense, this protocol is very efficient, where the verifier complexity is just logarithmic to the size of the Boolean hypercube. And at the end of the protocol, it suffices now for verifier just check a single polynomial, a single random point at its polynomial, rather than 2 to the n points for this polynomial. And after that, it suffices for verifier to convince the sumcheck statement holds true. So in some sense, you can view this as also as a reduction protocol, right? Which is a reduction from the sumcheck statements to some random evaluation statements for the same polynomial. And this is the only thing that you have to remember in order to understand the following slides. So now let's get back to our questions about this range proof protocol. And let's get back to this first step where you want to rephrase these statements into sumcheck statements. So the range proof statement is trying to argue that for this vector, committed vector, you want to argue every entry is in the range -b and b, right? And the first step is to translate into an algebraic check. To do that, we define this polynomial h with the product of these terms. And the nice property here is that h evaluated at x equals 0 if and only this integer input x is in the range. Why? Because if it's in the range, one of the term will be 0, product will be 0. Otherwise, the product will not be 0 because every term is non-zero. And then we can also, so that means now we can translate this to argue that for every entry fi, h evaluated fi is 0. And we can also replace this integer arithmetic to prime field arithmetics, and the scheme, the argument will still hold true as long as the prime field, its prime modulus is large enough. And the next step is to translate this statement about vector into a statement about polynomial. So the idea here is to embed this vector f1 to fn into some multilinear polynomial. So multilinear polynomial means a multivariate polynomial for which the degree of each variable is at most 1. And you embed this vector as the evaluation of f in this Boolean hypercube. So that means the evaluation of f at points 0, 0, 0 will be f1, and the next point will be f2, and finally the evaluation of 1, 1 will be fn. And now you can retranslate the original algebraic check as following, right? Given some multivariate polynomial h of x, you want to check for every point in the Boolean hypercube, it evaluates to 0. And then finally, there exists some very classical transformation from this zero check problem to sum check problem, given techniques from Hyperplanck and Spartan. And finally, you obtain the sum check statements, which want to argue that the sum is 0 for some polynomial g. Okay.
Do you require the small b to be like small so that the polynomial doesn't blow up?
In principle, you can use b to be large, but that you are right. That means that this polynomial, this sum check protocol will be less efficient, but it's still like linear to b. But usually, this b is something you can choose, right? And in practice, you actually just choose to be 2 or 4, and it's actually pretty efficient. Yeah. Okay, so now we finished the first step, and second step is to build a phone scheme for these sum check statements. And our starting point is exactly this famous and classical sum check protocol, which gives you a very efficient prover time and verifier time. And here the prover time is linear to b times n, and the verifier time is logarithmic to the length of vector, n times b. And almost no constant overhead. And as you remember before, this reduced to a random evaluation check statements, right? And here we can do slightly better in the sense that because of the structure of G, which is basically just a product of some multilinear polynomial of f, can reduce to check the multilinear evaluation of f at random point r. And after that, the verifier can recover the evaluation of G afterward herself, given the evaluation of f, right? So now the question is how to check for this committed polynomial f, the evaluation at the random point r equals some claimed value, okay? And there exists a very naive way to achieve that. Well, the prover just sends the witness to the verifier, basically send this vector f1 to fn so the verifier can interpolate it and compute the evaluation herself. But this definitely is not going to be efficient, right? Because now it means that for the verifier needs to do this multilinear evaluation with complexity is at least linear to the vector length. But how to do that? And what we want is a very efficient verifier. And the key observation here is that I think also this is kind of, I think observed, but also some prior work. But here the key observation is that this evaluation statement itself is also easy to fold. So we don't have to let the folding verifier to check it right now. We can fold it and delay this check till the very end. So now let's see. Suppose we have 2 evaluation statements for some 2 committed polynomial f1 and f2. And our goal is to merge them into single evaluation statements. And to do that, observation here is that a multilinear evaluation statements can be represented as a sum check statements. And this is by this famous multilinear extension theorem, saying that the evaluation of f can be interpolated as the evaluation of f at a point in Boolean hypercube. So this is very similar to the univariate case, where in the univariate case, I think most of you are familiar with it, that a univariate evaluation can be interpolated using Lagrange polynomials. And here the EQ polynomial is some analog of Lagrange polynomial here. So now you have 2 sum check statements, right? And we know here that we have sum check protocol for that. And then we can merge these two sumcheck statements into one and run this sumcheck protocol. And finally, it now reduced to a single final evaluation check for some combined Martini polynomial, FFD. And this combined committed polynomial is just a random combination of the previous committed polynomial F1, F2 using some random scalar rho. And now this new random point is just the fresh sumcheck challenge vector you had. Okay, so that leads to our final solution. Well, we finally will need expand this commitment open relation a little bit to also include these evaluation statements and set that as some accumulated folding statements. And at each step, you want to merge some online commitment open relation statement onto it, right? And that's basically just a random combination plus this sum check for proving these range proof statements plus these evaluation statements, right? And after that, now you can reduce to a folded commitment open relation statements plus this last Martinini evaluation check at the end of the sum check. And now we can use this as a new and updated folding statements to be used in the next step, right? And at the very end, the SNARK verifier will also check this final evaluation statement herself.
Okay, so here you basically just add the range proof to the theorem you're trying to prove.
Yeah, so basically, yeah.
And that ensures your extraction will work. Does that?
Yeah, that's the intuition, but it's slightly more complicated than that. But yes, so basically what you want to prove is that for these two, this involves some matrix multiplication relation and some range proof checks.
Right.
And this also involves some evaluation checks. And now, because you can interpret all these statements as some subcheck statements, you can run a subcheck protocol for that to make sure that the statements are holding true. And finally, because there are statements holding true, actually you can guarantee that the extracted witness will be satisfy those range proof statements and evaluation statements.
So it's not just like doing random linear combination. It's
more than that. Yeah, it's doing random
you have to
combination.
do like linear combination and also like the sum check.
Yes, that's true. That's true. So plus here is you need to do both. Yeah. And the key highlight here is the verified complexity is only still logarithmic to the length of the vector, which is still very efficient with almost no constant overhead. Okay, so that's the high level idea. However, in order to make it work and actually very efficient, you need to deal with a lot of subtleties and you have to make a lot of optimizations, which I won't cover here. One of the key subtleties here is that you have to instantiate everything over polynomial ring rather than integer, because the other commitments should be used over rings for better efficiency, and random linear combination needs to use a small norm scalar, right? But in ZQ, there's very few number of small norm scalar, but you have to choose it from a large set for soundness, for good soundness. So you have to choose it from a subset over polynomial ring to make sure it's large. So that means the sum checks needs to be over polynomial rings rather than fields. But this, we can still do it, and actually we can do it very efficiently. And second, we want to support this small modulus Q, which I mentioned previously, so that you can have very efficient CPU and GPU operations with no big number arithmetics, and you can be able to more efficiently pack this real world data inside these ring elements. And we can also achieve that with some adaptation and optimizations. So that's basically it. And now let's go back to the original question. We want to build a folding scheme for this MP relation, right? Actually, not just commitment opening relation. And now it's more complicated because we have to express these MP statements about chunk statements and folding verification. That means the previous relation is no longer sufficient. We have to augment it to support some MP complete language like R1CS constraint system or customizable constraint system introduced by Srinath, Justin, and Riyadh. And we also generalize this kind of notion from fields to also over rings, which makes it the perfect fit for some applications that all the operations are done over rings. For example, fully homomorphic operations or some of machine learning operations. And we also construct a folding scheme for that augmented relation, which is not too much harder. And after some transformation, we can still reuse this kind of decomposition plus folding framework. Okay, so some kind of words about this efficiency. Before that, any questions? Cool. So about efficiency, you can see here what's the difference. Compared to those existing Peterson-based schemes, first, we have replaced Peterson commitments with Ajtai, which means that we have removed those expensive elliptic curve scale multiplications and replaced those with some ring multiplications, which, as mentioned before, can actually be implemented very efficiently. And even better, there are tons of highly optimized libraries for FHE, and that means we can migrate those kind of like libraries into here to make this folding prover even more blazingly fast. Because some of the FHE scheme are exactly particular for doing some ring operations. And we also don't need to use very sophisticated stuff like bootstrapping. All things are very lightweight, okay? And in terms of this recursive folding verifier that we need to represent as a circuit, the dominant part is the sumcheck verifier that involves logarithmic number of hashes and ring operations. But here, compared to Peterson's based scheme, one of the great advantage here is that all the verifier operations are only over a single quotient ring. And that means every operation can be translated in the circuits in a native way. We don't need to do any non-native field simulations as being done in these Peterson-based schemes. And that's also one of the main reasons that actually this recursive circuit size can even be even better than those pre-quantum folding schemes. Yeah.
What do you mean by non-native?
Oh, yeah. So as I mentioned before, you need to represent some field operation of field F1 using some arithmetic circuits over field F2, where F2 is different. And that's actually pretty expensive. But here, every operation is over RQ, so you can just represent them as an arithmetic circuit still over RQ. So it's very efficient and succinct to represent. Yeah.
Do you need a cycle of those, or is that like?
No, we don't need to cycle. Yeah.
That's
Just
good.
yeah. Okay, so that's about folding. And after applying this piecemeal construction compilation, you obtain a final folding statements that verifier will check. However, usually in practice, suppose you initially have some very large NP statements, say 2 to the 40 or 2 to the 32, then even if you split them into many chunks, each chunk statement still will have some relatively large size. And that means this folding witness can still be large as tens of megabytes. But this is actually pretty easy to handle using some very classical tricks where you just delegate this checking of folding statements again to the prover and let the prover to generate proof for this folding statement check, which is actually not too expensive because now this is just for a chunk statement size much smaller, right? And that if you use, for example, post-quantum secure SNARK for that, then you obtain some proof size of less than 100 kilobytes and it takes less than 2 milliseconds to verify. And if you don't care about post-quantum security, you can do even better. You can use some KZG-based scheme to make the proof size to be as small as 1 to 5 kilobytes, which is even better. Okay, so that's basically it. The key takeaway here is that we introduced this first lattice-based folding scheme based on Ajtai commitments that leads to this memory-efficient post-quantum secure SNARKs that has a blazingly fast prover and small proof sizes and cheap verifier. And one of the very interesting and challenging open problem here is that whether we can have some compressing plus linear homomorphic commitments in the lattice world that has no norm constraints. Okay, if you don't have these no normal constraints, LatticeFold is actually useless. You can forget about LatticeFold. You just do some random linear combination as in Peterson commitment scheme, and you can enjoy the advantage of using lattice commitments for fast prover and native circuits. But it's much simpler. The scheme is almost the same as Nova, and everything should still work out. However, I found that to be very, very challenging problem because usually if you use SIS assumption, you have to run into some norm check somewhere. So this is a very interesting open problem, and it's very useful as well. And secondly is whether you can do folding for a wider class of relations. For example, is table lookup relation, which is very useful in practice in blockchain. The problem is just first checking for some secretnesses that's in some pre-processed tables. And this part is, I think, is highly feasible because of this recent work of Lasso, which gives you a lookup arguments from sumcheck. And their framework is actually pretty compatible with LatticeFold, so we believe it's actually pretty natural to support that as well. Okay, so finally, let me mention one concurrent work. Well, after we publish this, there exists a new work that by Benedict, Pratush, and Wilson and William. They built this semi-folding scheme that's purely from hashing. You don't even need to use Lattice crypto, even though in our case, this Lattice crypto is still very lightweight. But if you only need to use hashing, that's even better. It's even faster. However, they have some trade-off about this. And that's why I call it semi-folding scheme, because they have much larger recursive verified circuits, because they have to perform really many hash operations inside. And secondly, they only support constant number of folding steps. If you fold for more than constant number of steps, there actually exists some concrete attacks for that. Whereas for Nova or for Protostar, for Hypernova or for LatticeFold, those kind of attacks will never work. Okay, so that's basically it. And yeah, thank you for your attention. And yeah, great to be here. And I'm happy to take more questions.
I have a question. So for this scheme, when you fold it, do you need to know the witness to get the for the commitments and the witnesses?
Yes, as a prover, you need to generate the witness. But yeah, the folding prover will generate both the commitments and the witness herself, and fold both the commitments and the witness. Yeah.
And here when you mention SNARKs, you mean SNARKs with the proof size is linear with the witness size,
Yeah, you mean before this classical compression trick, right? You're saying?
yeah. Can I just talk about SNARKs instead of folding? Yeah.
Oh, you're saying this, right?
Yeah.
Before this compression.
Yeah.
Yeah, you're right that this size is linear to the chunk statements.
Mhm.
And the witness is just for a chunk,
Okay.
the witness of the chunk statements rather than the initial large statements. It's much smaller than the initial large statements. For example, suppose you initially the large witness is say, like 1,000, and if you split them into 1,000 chunks, then the chunk statement's witness is just one, right? That's a class toy example. So actually, it won't be too large, but still, if you like initially this is very large, then finally this witness size will be not too small. So you have to use this extra trick to generate the even smaller proof. But that doesn't add too much overhead, because the statement size you want to prove is already very small compared to the initial statement you want to prove. Actually, yeah.
So I have a question.
Mm-hmm.
Yes. So when you instantiate this with like Fiat Shamir and like actually implement it, do you need to rely on this sort of heuristic instantiation of the random oracle?
Yes, that's true. Yeah. So we focus on this concretely efficient scheme, and almost all this existing folding scheme needs to rely on this heuristic random oracle assumption, I think, from Nova, Protostar, Hypernova, and LatticeFold. So yes.
Okay, thanks.
Yeah, so I was a little confused to like how you did the sumcheck folding. Can you explain that in a little bit more detail?
So what do you mean by?
Like where you fold to, yeah, this. Yeah, so you take two like polynomial evaluation statements and then you convert it to a sum statement, each one of those, I assume, using the multilinear extension.
So you actually have, so here there correspond to one evaluation statements, right?
Okay.
And here there correspond range proof statements.
Okay.
Right? And here's another range proof statements.
Yeah.
And that all can translate to a sumcheck statements.
Oh, yeah, so I was specifically talking about the one on top, the picture on top.
On top?
Yeah.
Here, oh, I see.
Yeah, so yeah, how do you translate those polynomial evaluations to like a sumcheck statement?
Oh, yes. So here, the
Yeah.
evaluation, single evaluation is that sumcheck statements.
Sure.
And you just randomly combine this F1 F2, and it's a single random evaluation statement.
Okay, so you randomly combination of those two sums.
Yeah.
Okay, that's,
Yeah.
okay, great.
Hey, any other question? So I just stop share.
Yeah.
Okay. Okay.